Okay, so couple of things for those of you who are attending or see it later. The DimDim actually is no longer available publicly, so it's getting sold out. And so I need to figure out whether the Wimba web session at ePoly works or not. So next week, which probably will be our last DimDim session, unless I pay for my license, which I don't want to. I think Poly should pay for it, since you guys are paying a tons of money in tuition for it. So at any rate, so I'll try to see if the web session at Wimba in the Blackboard works. If it works, then we can then switch from DimDim to Wimba. And once it's in Wimba, I'm hoping that I don't have to go through all that mega upload and downloading and uploading, and it's a pain for you guys and it's a pain for me. It's just not a good use of either of our time. So that's what I wanted to say. So you expect some email next week from me, and let's try to see, how the Wimba works, or maybe I can reach out to ePoly to see, if they can give me some instruction. So that's that. So for today's agenda, basically, we want to get into a rhythm now where we just purely want to review codes and understand Bioconductor, which is the reason you're taking this class. So at the start of today, we will review the first section of the homework. I had a chance to look at most of your homework, and all of you did very well, so I'm very pleased to see that. So I'll probably give you a grade by Sunday with some comments to it, and I'll be posting the assignment 2 tomorrow. But I wanted to cover with you some pre-work that you need to understand before you can actually start working on assignment 2. And that's the only reason I did not post it earlier this week. So I wanted to meet with you guys before I post it. And I'll tell you what the due dates are. So I tried to do it for the remainder, like every 2 weeks you should have an assignment to submit. So at the first, we will cover the first section of the homework, right? Not the script. Maybe everybody pretty much got it, but I'll try to do it at the end if we have time. Then I want to make sure that you guys understand the most critical part in chapter 2, which is how can you start from scratch, right, with the text file, and how can you build your expression set. And what do you mean by all this class and object, and what does data, feature data, all that means? So if you don't understand the fundamental structure of how Bioconductor works within its classes, in the future homeworks, I think you may find it very difficult to what code you actually need to use and how are you accessing. So what we are covering today is pretty much will be the foundation of Bioconductor. Probably would have been better suited to do that last lecture, but at any rate, we're going to do it now. So hopefully if you had a chance to got some exposure to Bioconductor now, hopefully you are reading chapter 2. So once I cover it now, which is pretty much what I copied from chapter 2 and one of the vignette that was available for bio-based package, so it will probably make more sense to you. On the third section of today's lecture, I would like to go over what I couldn't do last week, which is go over a sample code of the simple AFI package, right? Because last week I think what we showed you is you read a cell file, you looked at the structures of the object, you look at some properties of that object, and you looked at a sample intensity. So you basically ended up concluding that for this file, for that feature, what was the value, right? So that's something we did last week. So you will get probably a more deeper understanding of how reading the data and how the object of the microarray data works once I covered that. And then finally, if we have time, I will do the last part, which is the last section of the homework, which is I pretty much gave you the whole solution. You basically had to just put them together. But if we have time, we'll just execute those lines and I'll talk through it. So if you have any question, you can ask me later, or maybe it will just help you to have a better understanding. So that's the premise of today's next hour and 50 minutes that we have. I'll periodically try to look at any comments that if you have, but we don't have that many attendees, so I'm assuming you're watching it later. Or, if you have questions, I always expect an email from you. So let's maximize the screen and let's review the first part, which is our first section of the homework, which is very, very easy, I thought, the homework that was given for first one. Okay, so let's go through each of them, and I know some of them will be a repeat and bored to you, but I try to do that, easy or hard, I try to go over the solution. So first one is we want to create a vector from 1 to 4 and assign it to x, right? So vector is either can be a character or could be number, right? It's a single data type. So by C we can collect all this 1 to 4 and we can assign it to x, so x becomes a vector as you see in my console. And let me just minimize that here and bring the console here. Okay, so now x, let's look at x. So x is now 1, 2, 3, 4, so that's an atomic vector, or rather to say atomic numeric vector, because the data types are numbered. Now I'm asking you to access the fourth and the fifth element. There's actually no fifth element, right? Because the fourth element is the last one. But at any rate, if you do that, like the 4 and 5, it accesses the fourth element, right, which is 4, and the fifth element is not available. But when something is not available, R doesn't bomb on you. In some program it would just not work to say I didn't find it. It'll probably throw an error, but R will just simply say it's not available. So that's why you get NA. Okay, so now you have a vector data type, which is x. So what I'm asking now is to convert that object vector into a matrix, a 2 by 2 matrix, right? So 2 rows and 2 columns, and the way you can actually convert something into a matrix is you use the dim operator. So if you do the dim operator on x, now x will become a matrix, and you want to have 2 rows and 2 columns, so that's why you have collection of 2 by 2. Okay, so you have the existing x, you put dim around it, so now it becomes a matrix, and it should have 2 rows and 2 columns. So now you can just see 2 rows and 2 columns, so you have 1, 2, 3, 4, which was the existing x as a vector here, but by using the dim around it, you have converted the object from vector to a matrix. Then you can look up, what dim name does, when you do the question. So I know that all of you did that. And what I'm trying to ask you here is right now it doesn't have a name over it. It gives you the index of what the elements are. So this is saying the first column, second column. This is saying the first row or second row. So that's sort of giving you the index, but it's not telling you any label. And the way you can assign a label to a matrix is you can use the function's row name and the function's column names. So if you use row names x, then you can collect row 1 and row 2. So it will sequentially assign row 1 here and row 2 here. Similarly, for column names, you can do column 1, column 2 to sequentially assign column 1 and column 2 there. So let's do that. Very simple. And you can find that you need to use row names and column names to assign the name when you did the question dim names. So when you did the question dim names, at the end of that help section, there was example from which you can tell these are the 2 functions that you have to use. So I did the row names here, and I did the column names here, and then let's take a look at x now. So now x has some names assigned. So you have column 1, column 2, row 1, row 2. Very simple. So that ends the section 1 of the homework, or the first one. So I basically go through each data type, each object type, so just to make sure you're getting familiar with each of this object. Because once we get into bioconductor, we start with these basic objects of frames and factors and matrix, and build more object on top of that. So if you don't understand from the very simple level, it only gets more complicated because you build things on top of things. It's like building a house. So if you don't understand what the brick is, then you're not going to understand what the walls are. If you don't understand the walls, you're not going to understand how the rooms are, and on and on. So important to understand it, from the very simple concepts. Now factor says the first thing I want to do before I get into factor is I want you to generate a random number letters from 1 to 5, so A, B, C, D, E 10 times. So it could be like A, B, B, then C, C, A, whatever it is, right? So to get consistent result, you can actually set the seed to be 1, 2, 3. So all of us will get the same thing, I'm assuming. And then I am creating this X where the letters will be from 1 to 5. I want 10 of them, and I want the replacement to be true. That means I pick the letter A. That doesn't mean A is out of the question anymore. So I'm putting the A back into the hat. So A can be again pulled. So that's what it means by replace equals to true. So you did that, right? So X. So now let's look at X. So in our case, by setting this seed, we get B, D, C, etc., etc. So this is actually X right now is a character atomic vector, right? So what we want, just like the way we showed you in the first one, you converted the vector into a matrix. Over here, I want to convert the vector into a factor. right? On factor, remember, we use factor whenever we have a distinct or categorical data. So over here, E is repeating many times, C is repeating many times. So fundamentally, the level that you have in your data set is A, B, C, D, E. So these 5 letters can actually represent all of these here. So that's factor, and I talked about what benefit factor has in as far as storage and assigning number to it. So instead of using some different strings, you can just store everything as 1 2 3 4 5. So that's why you want to have factor. It has a more efficient storage in R. So same concept like we did from vector to matrix. Now we're doing from vector to factor. So we did that. So now let's look at factor. So once you look at the factor actually gives you all the values that you have, 10 of them. Then it gives you the levels. So what are the distinct elements that you have in your object. Then you can actually also display that by putting the attributes character around it. So if you put attributes of y, it tells you what are the levels, right, of your factor, and what is the class of your object y. So the class or the object of y is a factor. So remember, class is the template and object is the instantiation of that template. So third one is the data type called list. So the difference between vector and list is vector only has one type of data element. So it's going to be either all numbers or all characters. But in list, you can have a mix and match. So over here, I'm creating a list of numbers on the first 2 elements, and the third element is a character. So let's create the list, which is Z, right? And now let's look at Z. So Z actually gives you 3 different elements. So number 1 is the element A, element B, then element C. These are data types of numeric. This is the data type or object vector of character, or data, right? So that's the list. Now I want to show you what are the names of the elements you created. So the names are basically A, B, and C, right? So these are the names. So if you only want to get to the names, but you are not interested at the data that's under the names, you can just simply use names Z. Then it will tell you this is the distinct elements or the name of the elements that you just created on your list Z, which is A, B, and C here. Okay, moving on. So now we want to construct a frame. So frame, as you remember, is a type of list. So data frame is a list. The difference is in a frame, it's sort of like a rectangular grid where you have the same number of, in each column you have the same number of rows, right? So that's the frame. So in the first column, if you have 3 rows of data, second column will have 3 rows of data, and the third column will also have 3 rows of data. But each column can be different data type, right? But the number of rows under each column is same. So think of it as a rectangle. So that's called the data frame. So let's say there are 7 or 6, whatever students in our class. So what I'm asking you is first you create some IDs for it. So think of each of these elements that you're creating in the data frame first as a vector. So you have to create the student ID. So that could be simply a vector where you can say X is equal to 1001 to 1007. Then the second one that you will create will be a character vector, right? So you're going to basically assign bioinformatics, biomedical, and biostatistics. And the third one is also going to be a character vector where you're going to have 2 elements, online and in campus. Then what you're going to do is you're going to put all of them together by putting a C, right? And then you're going to convert it to a frame. So let's go through each step at a time. So if you break down the problem into smaller chunks and then put them together, that's the best way to attack a programming problem. So first thing is I'm asking you to create an ID, right? 1001 to 1007. So I can easily do that. So that's just no different than creating 4 elements, what you saw in the first. X is 1 to 4. Here ID is 1001 to 1007. Here it's a little different, but I already gave you the hint that you have to use the ref function, which is repeat. So what I'm asking you is you have 1001 to 1007. So there's 7 of them. So there are 3 students in bioinformatics, 2 in biomedical. So 3, 2 is 5, and 2 in biostatistics. So that's 7. So you cannot just simply create bioinformatics, biomedical, and biostatistics. Then you'll have 3 elements. So you want to create the bioinformatics 3 times, biomedical 2 times, and biostatistics 2 2 times. And the very easy way in R to accomplish that is to use the repeat function or ref function. So in the ref function, you first supply the parameter of what your string is. Then on the second parameter, you tell how many times you want to repeat it, right? So then let's run it then. So now if you check your department, which you can easily do that, then you can see bioinformatics repeated 3 times, biomedical repeated 2 times, and biostatistics repeated another 2 times. Again, your status for online and in-campus cannot be just 2 elements. You have to repeat online 3 times and in-campus 4 times. So 3 and 4 is 7. Here is also 7, and IDs is also 7. Remember, you're constructing a data frame. So if you have 3 columns, ID, department, and status, so under each row, they all have to match up. You have to have 7 elements here, 7 elements there, and 7 there. So we do the same thing when we create the status. So status, you should see, also have 7 elements. Okay, so now let's put them all together by a column bind, right? So when you use the function column bind, right, you put ID is ID, department is department, and enrollment equals to status. Let's see what happens. So now let's see what's the class you just created. It's a matrix, right? So whenever you use a cbind, that function actually puts ID as a column, department as a column, and enrollment as a column. So these are the names, and what you're going to give as value is the vectors that you already created here. So ID, department, status. So you created 3 individual vectors. From vectors, you use the function cbind, right? So by cbind, you actually created now a matrix. But I'm not asking you to create a matrix. I'm asking you to create a data frame. So the way you then do the data frame is you actually take the matrix, right? And you write a convert function to say as.data.frame. So this is very simple, right? So in the past, you converted a vector to a matrix. You converted a vector to a factor. Here, you're converting a matrix back into a data frame. So you have to be very comfortable, to first understand what's the fundamental object that's here. And you have to know how to convert something from one object to another object. Okay? So that's what you do here. You convert your matrix that you created here to a frame. Now verify that what is the object now? Is it frame indeed? Indeed, it is data.frame. Okay. Let me see if you guys have any question. It is not. Okay. Now, what I'm asking is I want you to sort, right? So let's just look at students here. Let's check this out. So this is how students are, right? You have bioinformatics here, enrollments here, in campus or online, and these are the IDs of all of these students. So I want you to now sort it by department. So if you want to sort by department, the way you can access an element, right, and we'll talk about accessing in a bit. So if you want to access just one column out of these 3, then you can use students $department. By doing that, you can access this particular department. So once you get that column, which is students $department, around it, you call the function order. So order will then actually alphabetically order this particular department. So now, if you do that, actually just the way I wrote it, it doesn't make any change because alphabetically is still the same. But I could have also done the ID, but this is already coming as sorted. But just the way to show you, how you sort things. Now let's get a little bit interesting, which is now I want to know from this table that I have, what are the IDs of the students that are taking online class. So I can tell just by looking at it that it should be from 1001 to 1003 who are taking online. So what you will do there is you access this column student.enrollment, so that's your column, and the condition is equals to online. So if you do that, then you should only return 1001, 1002, and 1003. So then what you want to do is this function here, the accessing element, right? So that now gives you 1001, 1002, and 1003. So first you give the condition, who are onlines, right? And second is you want to give the ID. So only from students you actually get those IDs that belong to online. So first parameter is the condition, second parameter is of which column you want to access it, and that's how you actually subset the data. And then many times on your analysis you kind of want to know that, right? You start with a lot of genes, 25,000 features, then you want to put some condition around it to say out of this 25,000 probes, show me those probes that may have an intensity greater than some threshold or p-value less than some threshold. So understanding this at this time, how to access and subset your data, is going to be very critical when going forward you're going to do more and more of this analysis on your homeworks. Now what I'm asking you is to tabulate the department by status, and I want you to use already told you the function to use, which is table. So just to get to the status, I told you the name of the column of the status is enrollment. So all I have to do is access the column, which is students $enrollment, and I put a table around it and see how it tabulates it. So it will tell me that in online I have 3 students, and in campus I have 4 students. So tabulation or table is a very handy function in R, which kind of gives you a summary level data. So you don't have to really write a apply loop or for loop or do some count to figure out how many in online and how many in campus. You can just do a simple tabulation type format. So hope you find this kind of things handy. So that is ending what we wanted to know about data.frame. Now let's move on to matrix. So I want you to create a matrix exactly in this order. And I noticed some of you created the matrix, but your 1, 4, 2, instead of being a row here, became a column. So when you go back to your homework, make sure that you binded it correctly, because I am expecting you to create this exactly how I'm showing you here. So some of you actually missed that. So hopefully after this review, you will know how it needed to be created. So what I want to do is column bind here, right? So remember, you can create a matrix by cbind or rbind. When you use a function called cbind, right, it will create a column first. It will create this one first, second column second, third column third. If you want to do a row bind, then you have to do 6 times because you have 6 rows. But since you're doing a column bind, you actually have to do it 3 times, right? First, second, and third. So this is sort of handy. You don't have to be very fancy with these things. You can just say collection of 3 1s and 3 2s. But it's just if you're interested and if you're playing around with, you can again do it by the repeat function. So what I'm saying is I want to repeat from 1 to 2, and each of them will repeat 3 times. Right? So 1 will repeat 3 times and 2 will repeat 3 times. So I can very easily construct that. Fancy way to do that. You can very well do that by typing 1 1 1 2 2 2. Just showing you. C should increment from 4 to 6, and second one should increment from 1 to 3. And this one I just didn't find any pattern in it, so I just collected all the elements here. So these are the 3 elements. So each of them represents a column over here. And since I'm doing a column bind, they should all add up one after another, right? So that's what I do here. I'm sorry. So let's create the matrix by column and verify that the matrix that I created is exactly what I requested you to make in your homework. So that makes sense. You have 1 1 1, 2 3 2, and looks all right to me. Now what I want to do is I want you to add a 4th column on your matrix. Again, just use the column bind function, and I want you to use these numbers 13, 10, 17, etc., etc. So then you just use the column bind again on your existing matrix, which is Z. So you start with Z, and on top of that Z you do another collection, right? So you take something and you build something on top of that, and that's how you add the 4th column. So now if you look at Z, it should have the 4th column. So everything's looking good, and we already did that before. So now why don't we do something? Why don't we give some names to the columns? I want to give the first column should be type, week, ID, and height there, and maybe I want to do some categorization. Maybe the first 3 rows belong to type 1 type of data, and the last 3 rows maybe belongs to type 2 type of data, and then maybe we'll do some plotting on that just to take it to completion. So let's do that then. So column names, again, we showed that to you before. Of the Z, the matrix that you created should be a collection of these 4 character vectors, right? So then the column names gets assigned, and then the row names, I think I also do as type 1 and type 2. I don't know where I do that, but I have to do that. Okay. Maybe I deleted that. Okay. So row names of Z should be a collection of Okay, never mind. I'm not going to give you row name because in this column, actually, I asked you the type name. So this is the first three, subset of data, and the type 2 with the three subset of data. Sorry, I didn't want it to subset it row wise. But if you wanted to, you could have also done that. So now let's look at Z. So this is how it looks: type, week, height. So the column names get attached. Now I want to break up the data first by this way and the second by the last three columns. So now you can also access a certain element or change certain elements. So what I'm telling you here, on the second row and the fourth column, right now the value is 10. I wanted to change you to 50. Very simple. You just say Z, which is second row and fourth column. Z24 should be 50. So initially it was 10. So now look at it. So now 10 is getting replaced by 50. So that's how you can access a specific element within your matrix. Now I want you to sort this matrix by week and by height, right? And store it into a different matrix called Z1. So right now it's 4, 5, 6, 1, 2, 3, but I want it to be 1, 2, 3, 4, 5, 6, right? So that is very easy. You can actually sort it by order the Z with the second element and then the fourth element. So this is first, second, third, and fourth. Okay. So let's just first figure out what is the class of Z. Must be matrix, right? So the class of Z is matrix. So if it's a matrix, if you actually wanted to do it by Z $week, you will not be able to do that. So the Z $week, I also showed you earlier where you're actually using the dollar operator, remember? So what works here is you can actually use the dollar operator. You can sort it by Z $week when this is a data object type of frame. But when it is an object type of matrix, the dollar operator with the version of R that I have does not work. So you can try it. If you want to order it by Z $week, you'll get an error saying dollar operator is invalid for atomic vectors. So when it's a matrix, this is the way you will actually order it. So let me show you Z1. Oops, sorry. Z1. So now it's got sorted, right? 1, 2, 3, 4, 5, 6. And comma 2 means, always remember, the first index over here is for the row index. Second index is the column index. So second column and the fourth column. And that's how you sorted it. But now, how do we use the dollar operator there? So again, I showed you earlier. Let's convert the matrix into a data.frame. So I take the Z and I convert it to a data.frame. Verify, what my class is now. It is an object type of data.frame. And now I can actually use the dollar operator. So I can just say order Z, right? So I created Z matrix and converted into a frame and stored that into a Z frame. So Z1 was a matrix, but Z frame is now a data.frame. Right? And since it's a data.frame, I can use the same function, but instead of using this indexing operator, and I'll show you later what's the difference between single subset, double bracket subset, and a dollar subset. But you can only use the dollar subsetting when it's a data type, object type. Sorry, sometimes when I speak too fast, I confuse between data type and object type. Remember, in R, everything is an object. So if I misspeak, then you know I meant an object. So now you can actually use the dollar operator because I converted it into a data.frame. So that's my Z2 and I can verify it, right? So here I have my type 1, type 2. It's all sorted by the week and I can actually use the dollar operator. Okay, so now we're going to do some plot, based on the data that I have. Maybe I want to plot only the subset of my data.frame when the type is 1. And maybe I want to plot when the type is 2, and and maybe I want to make 4 plots, right? So I want to make one plot just for type 2. Maybe I want to make one plot just for type 1. I want to make one plot where I'm combining the type 1 and type 2 into single plot, and I want to make the last plot with some kind of fancy labels and different colors and etc. So one function that's very, very handy, and I didn't get to cover it the first time I met with you guys covering the teaching R slides and whatnot, is about the plotting and printing. So now it's a good time to do some plotting and printing and show you some of the very amazing capabilities that R has, and you'll find it so useful when you're trying to summarize, plot, and present the data, for your publication or to your management or whatever it is that you're trying to do. So when you set this parameter, mf row is a collection position of 2 by 2. So basically you are just establishing a grid with 2 rows and 2 columns. That means you have 4 slots or positions where you can print it. And when I show it to you, it'll probably make more sense. So you're preparing it within the same page. You're now displaying 4 plots. So 2 rows and 2 columns consist of 4 plots. So that's what per MF row C22 means. So this has activated your device. You haven't still printed anything, but it's ready to take 4 plots over here in this single page. So what you want to do now is the first 2 plots that you want to do is you want to plot it by height. So now I have my Z2 over here, right, which you can already see here. So I want to plot the Z2 dollar height. I only want to plot that against the type, and I want to create a box plot. So if I do that, you can see 2 of the plots got created over here. So the first one is for the type, okay, of let me show you the object again so you can visualize. The first box plot is for type, I think it's for type 2, right? No, type 1. So for type 1, the value is from 13 to 50. So this is your 13, the low value. Then you have your 50 over here. And I only have 3 values, so it's going to put 3. So this is your low, this is your high, and this is your medium, which is 17. So that's 17. So that's type 1. And the second one is type 2. So you have your low of 10, high of 20, and your medium, which is 12. Right now I don't have any label or anything. But now that I have used this tapply function, so you have to be careful on about tapply, sapply, eapply. There are different apply family, what we call, of functions that's available. So what R is very handy. You always want to use the apply family of function when you don't want to do a for loop and you want to group things. So just because you use the tapply function here, what it did, it looked at the height, but it looked at the distinct value of type. So on the second argument, it knows that there is type 2 and there is type 1. So because you use the tapply, and I gave you a hint to use the tapply, it actually broke out your plotting, one grouped by type 2 and one grouped by type 1. And you really didn't have to do any other for loop or anything. So I highly recommend that you question and find out what's the difference between tapply, eapply, and sapply. So it all depends on what type of object that you're working with. Now second one is I want to do the third plot, so which probably will get printed here, and I want to plot the height against the type, and I want to do it within the same plot. So over here, both of these are individual plots, and that's how tapply worked. It first processed 2, then it processed the 1. But over here, since I did not use any tapply, it just plotted height against type, and it plotted both of them within the same box. And now the last one is now I want to print it with some kind of labels. So I still want to plot, and this is the why it will get printed, like the 4th position. So over here I still want to print the same, but maybe I want to outline the outside color a little differently. Maybe I want to give it a subset header over here. Maybe at the bottom I want to give a header. I want to give a label to my x-axis here to say it's a label. Maybe my y-axis will have value, etc. So when you look at your box plot, right, so box plot actually had many other arguments. When we just simply plotted it with the minimum requirement parameter, it did not do anything more fancy than I had asked for it. But now if I want the plot to be colored with red and green, maybe I want this one to be red and that to be green, maybe I want the border to be blue, my X label to be type, my Y label to be height. So then what I can do is I can use these additional parameters, and I can use them. And when you use the main function, it actually puts everything as a header. And when you use, sorry, not the function, the parameter, and when you use the sub parameter, it will then print something at the bottom. So some of these are not required, like you can choose not to use this, you can choose not to use this. So you always have to understand within your function what's the required parameter and what are optional. So you know that you at a minimum you have to say on your box plot you want to plot which column against which column. So these first 2 is always required. Anything else you're trying to do here, whether it's the color or bordering or height, etc., that's optional. And the best way to know what you need to do is, again, as I say over and over again, you do a question box plot, It tells you what are the different parameters are. At the bottom there will be an example, and that's the way you can learn how different functionalities are used in R. So let's just print the very last one just for printing's sake. So now you see the fourth one got printed. Like very nice presentation of colors and bordering and headers and everything. So it's so simple to do this and present it so nicely compared to many of the things you may have been doing with Excel and whatnot. So that's how I originally meant by par mf row, right? This over here, 2 by 2, just because you set it by 2 by 2. So it's a 2 row, 2 column. You use the same landscape or same print, but you are actually plotting 4 prints here. If you want to plot 2 prints, so you just say 1 1. If you want to do like 6 prints, maybe you do 3 3. Whatever fits in one page and that you want to do. Okay. Moving on. Number 6 is I wanted you to understand how to load some kind of data sets that comes with a sample. So in R, in Bioconductor, you'll see when you download a package like AFI package or annotation package, the best way to sometimes learn most of this package is with some data sets that's already available with the package. So you can actually upload the data sets and play with it and see how it works. So that was the intent of this last section. I guess this is the last one, right, of 6. Import something that comes as available data and see how it works. So the way you can actually load this data set that's actually available within the R, you don't have to import any additional package and etc. for it. You just call the women data set by data women, right? So once you do that, you can actually find out what's the class, right, of this thing that you just imported right now. So it's a frame, all right, so it will have some columns, have some rows, and each column will have the same number of rows. So, but and then there's a difference between, what's a class and what's a mode. So mode gives you a lower level of the object from which it's built off. So you can actually question mode and, figure out what it is. It's more of a is type of or what it is, or what is the storage, what is the type of this object. That's also mode. So if you do the mode of women, it actually tells you it's a list. And I remember I told you data frame is a list. So even though data.frame is the object, but its more root object that where it's built from, or a primary object, is list. So that's what mode gives you. You can also use type of, right? So type of also gives you list. So that's class, mode, type of. These are the 3 different functions that you can use to find out, what's the structure, sorry, not the structure, what's the type of object that you're dealing with. So then you can also go into the structure, which is str always, right? We'll show you a lot of this functionality of str when we get into Bioconductor. So it's telling you that it's a data.frame type of class, and out of that class, it's made out of 2 columns, which is height and weight. So and height is a numeric vector and weight is a vector. So when you start to investigate, it's the weight, which is a vector, height is a vector. You put them 2 together, that becomes a data.frame, which is actually also a list. So again, understanding what something is made of is the most critical if you want to become a very good R programmer, and I'm trying to strive there still. So that's the structure of your object women, and the length is, you have 2 columns, so that's what it's showing you. It's 2 columns, and the dimension means that you actually have 15 rows and 2 columns. So, but let's just look at the data set, and we can just simply type women. So that's what it is. So we have 2 columns, and so we have 15 rows. So that gives you dimension. You already saw that it's a frame type of object. And this is a height vector and this is a weight vector. Put them together, becomes a frame. Again, you can also see what are the attributes. So attributes again tells you what are the name of the columns and what type of object it is, and what are the values that you have, what are the names you have on your rows. So this gives you row names, this gives you column names, and this tells you what type of object you have. So you use this attribute, class, mode, type of, string to figure out what has someone built In this case, it's pretty simple because you're still talking about very primary object. But when you talk about bioconductor packages, because they're building objects on top of objects, so in bioconductor, you might take a frame, you might take a matrix, and you can just put all of them together and create an expression set object. So when you're first trying to learn it, you're not quite sure. So what you will do, you'll use functions like string and class to investigate and figure out, okay, how was this built? And that's the beauty of object-oriented programming. You start with something and you can actually use that and put them together with another object and come up with your own object. So you don't reinvent the wheel over and over again like would be on a function-oriented programming. So once you get that elegance and appreciate that beauty of the object-oriented programming, then you will appreciate, C++, Java, and to the point that, we're covering R here. Okay. So now just some very simple things, which is, I'm asking you now that, this is your data frame. So let's just figure it out from this data set, those who have weight greater than 120 and or maybe less than 150 pounds, right? So we just a similar one we did with ID when we did the students. So you refer to your women object and you just say that your this column each time, this is the data.frame, so you can definitely use the dollar. So you refer to the first column to say second column, so weight is greater than that and less than that. So this is your AND operator. So this is the condition. So if you give that condition here of your weight, it's going to give you the height. Sorry, the weights. Okay. So now let's look at that. So it should give you all the subset, which is 60, 60. So since you left this particular second parameter now, it gave you the whole object back. So if you specifically wanted to get the height, then you could have used the parameter of the in parentheses heights, right? So that would have just given you height. But since this parameter, the second one, is null, it will just give you subset. So all you did here, you did a subsetting of data. So you started with this 15 rows, but they said, I only want to get those which is greater than 150 and less than, greater than 120 and less than 150. So that you got your subset. And this is very critical in your bioconductor type of data set, because you want to look and say, I want to only get those features now, which should be in a row, that has a p-value of greater than this and less than that. So that's how you actually go from a bigger subset to a lower subset. So this kind of conditional statements and how you go from one data set to a subset of data set, or also how do you access a particular element in your object, those are the very, very critical skills in get going with bioconductor. So now if I want to just specifically get the mean of my height column of this subset of the weight, so I can just access the height by dollar function and just put a mean around it. So it tells me the mean of my first column is 64.5. Now if I want to generate a summary report, the summary actually tells me what's the mean, what's the median, and of each of my column. What it doesn't do, it doesn't give you the standard deviation. So I wanted to see that the standard deviation, if I only want to see that, I can just use the SD column, so women dollar weight. And put the SD around it, so that now gives me the standard deviation. Okay. So then I ask you the question, what are the differences between this, one access element or two accessing element and the dollar, right? So if you have purchased this book, I recommend you get this book, but you can actually see that in section 2.5 at your R Programming for Bioinformatics. That section very nicely explains, what are the difference between these three accessing elements. So what you're doing here is subsetting, and some of you responded by saying it's indexing. Technically I don't agree it's indexing, because index is like a page in the back of your book. It tells you that how what, if you want to know at a certain item, what page you need to go to get that item. So index is more of a location of your data. So once you know the index, you can very easily access that particular data that you're looking for. By subsetting, all I'm asking here is you have an object of 10 elements or 12 elements. So give me the exact 11th element. So if you know the index, you can actually get to that element. But subsetting from a verb point of view is give me the subset of that particular element. So technical, but I'm not going to argue on that. So let's understand, what's the difference between single bracket, double bracket, and dollar brackets. And the best way to understand this is when you create this list and I do some changes, and I'll explain you how these two things are different. So first, let's create a list with y. Okay. So now let's look at y. So y has three elements. One is A1, B, and C. Okay. So if now I use y with a single bracket, right? The single bracket and a collection of 2 and 3. So that means I want to get the second element and the third element. So within this subsetting, anything that goes inside it is the index or the number that I want to subset. So I want to get the second element and the third element. So it will return me $B and $C. See what it does? It returns me $B and $C with its value 20 and 30. So when you are using this single subsetting, right, you can actually get any number. You can use if you don't use anything, and I haven't, let me see. It gives you everything, right, if you don't use anything inside it. So you can either get everything, you can get just this one item, or you can get two items, whatever you want. So it's basically you start with a list and the subset is also a smaller list. And there is no limitation of it. You can get all of it or you can get any number subset of it. So that's how the single element works. Interesting about dollar is I want to get a specific element. So I'm saying I have element A1, B, and C. And see what I'm doing here. I'm typing $A, and that's the big difference with dollar. I don't have any element called A. I have A1, B, and C. But what advantage you have when you use dollar is that it does a partial matching. So even if you don't have an element exactly called A, but A1 is the closest, so when you did $A, it actually returned you A1, which had the value of 10. Right? And with the difference between double bracket is it doesn't do any partial matching. It gives you exactly one single element. So you do Y, and you can just actually assign F to B. So now instead of B, you can say F. So they are the same thing. So when you say F here, or you could have also say B, it gives you exactly one single element, B. But if you say Y like B1, it's not going to do a partial matching like dollar operator did. So ultimately, dollar operator does the partial matching to A when you don't have an element as A, but you had A1. So dollar and this two bracket always works to get a single element out of your list, but not all of it. But if you want all of it or some of it, then you use a single bracket. To get specific element, you use double bracket and dollar. The difference between dollar and double bracket is dollar you only use for subsetting. Partial matching. And another thing we also saw, the dollar operator you cannot use on a matrix. The dollar operator you can use on a list, or you can use on a data doc frame. But the single subsetting you can use on a matrix. So those are some of the differences that you have. The last one is very simple, where I'm creating a function, ASCII, right? The way you create function, that's the syntax. So you are actually going to take any text like X, and you're going to put a dollar on top of it. So the way that you concatenate, so those of you who have done in Excel, concatenation or other, so our equivalent of concatenation is paste. So you're going to take X and you're going to concatenate dollar in front of it, right? But you're not going to have any separated by, meaning you don't have any space over it. If you put like this, then when you end up doing your function, you'll actually have $2, and it will actually end up like this. You'll have dollar and some spaces, and then you'll have ZZ. But I did not want that. I didn't want any space, so I will not have any separation here, right? So that's the function. That's the syntax of creating your function. And then now if I execute the function by supplying X, so in this case is ZZ. So ZZ comes here. So this is now ZZ that gets appended with dollar. So then when you return, function always returns a value. It returns me $ZZ. Okay. So I'm going to take a couple of minutes break, and I think this completes the review of the first section of the homework. Depending on how much time we have at the end of the next hour session, I will try to go over the molecular weight, which all of you got. but I'm going to upload the solution anyway because you just have to execute line by line. So I intend to cover it if I have time, but I think we have to move on to a bigger topic, which is into Bioconductor, and take you through how you actually construct something from scratch. And maybe there's a lot here, but let's see how much we can do in next hour. So let me take a couple of breaks so I can compose my couple of minutes break so I can compose myself. And so let's see if there is any question also. It's hard to talk non-stop for 2 hours. I don't know why I do it. I should stop doing this. Anyway, what happened to DimDim? Did it drop? So it's recording. Okay, so I think I got dropped off, but I didn't notice. But we're recording, so sorry about that. Okay, so at least both of you guys are there, and I didn't know when I dropped off. I just noticed it's not there anymore. Anyway, so I'm recording it. So let's move on to the next session, which is let's understand, how does this bioconductor and whole thing works, right? So first thing is as I mentioned, so far what we have been really talking and dealing with is we start with some very elementary R objects, right? Vector, data frame, list, matrix, and whatnot. So what Bioconductor does, it puts those objects together. So if you want to process some cell files or you want to do some analysis on those cell files, so what Bioconductor does, it creates additional objects. So your processing is enabled. And the way you do that is you actually import different packages from Bioconductor library or website. And I showed you some packages called Simple AFI last time. There's AFI. So the base package that was first created, it's called BioBase package. And I think it's a good idea to understand, how that BioBase package was created. And what I'm going to show you now is very simple from a text file of some microarray data, and how am I going to put that text file and the related information of sample for that text file, and how I'm going to construct an object based on the primitive R objects that we have, which are data frame and vectors and etc. So let's just first see what are the files that I created. So I created a text file here, and this is nothing fancy. It's not a cell file. So let's say you did an experiment and someone sent you some microarray data based on a comma separated file or whatever, right? So just like we did in homework in task 1. So here, this is how your cell file microarray data looks like. So you have your columns worth of samples, and your rows, there you have features, and each column is separated by a comma, right? So that's called the text file called expression-data.txt. So I have here 6 features, and I have here 5 samples. So that's my first file. My second file actually tells me what does sample A, B, C, D, or E means, right? So that is saved in a file called pdata.txt, and now let's open that. So on this pdata.txt, I am saying that, so it's the same thing, A, B, C, D, E. So these are my samples, A, B, C, D, E. So a couple of these samples came from female subjects, 3 samples came from male, and maybe the first subject was treated with drug, these 3 with placebo, the last one with drug, and maybe I have some another column called score where I'm telling you on a scale of 0 to 1 what's the tumor progression, just making it up. Maybe it's 88%, maybe it's 93%, or recession, whatever you want to say. So I have some additional information about my sample. So now we have to say, from our perspective of a primitive object, right? I can actually read this text file and I can store it as a frame. All right, that makes sense. I can actually take this object and maybe I can store it as a matrix. But then we want to put those different data types of frames and objects and construct an expression set object, which will always be a standard way of your data storage, right? And you can actually then work on that object to further analysis, to do your test statistics, to do your annotation, and etc. So I think right now, next hour, let's try to understand, how do we even start from that text file, and how do we put all of this information together. So what I'm showing you here is on the highest level, you start importing this package, which is biobase package. This package will create an object called expression set, right? So under that expression set object is actually made out of 4 different objects. It's made out of an assay data object that tells you the data, which is the expression data that I just showed you here. So you have your rows and columns. So if you want to store this, just the data itself, that can be stored in the object called assay data. Then the phenodata object can be stored where you have your phenodata that I showed you here. So if you read it as a, let's say, as a frame, then you can actually store it into your phenodata object. Then your feature data will actually tell you, which I don't show you in the text file here, maybe each of these features here that I'm showing you, the 6 of them. So what kind of CDF file they belong to, right? What platform did you do to? Or this particular probe, what gene does it correspond to? So those kind of annotation and what is your chip type you can store in feature data. And experiment data can tell you, which is a concept called minimum information about a microarray experiment, right? So what lab did it? What company is it coming from? What type of experiment, who did it, what's the contact address. So if those are some of the information that you want to store, you can store it in experiment data. So now this is where rubber is meeting the road. So you're basically starting to put all these things together, and then you're going to put a structure around it, and your top level class that you're constructing is going to be expression set. So now let's try to understand piece by piece. First, how do you construct assay data? How do you construct phenodata? How do you construct feature data? How do you construct experiment data, right? And then how you put all of these 4 together to construct your expression set. And now that you have your expression set, how do you access different elements and how do you move around it? And this is all covered on chapter 2, but I'm just taking an extra step just to go over it again, so it just makes it easier for you to follow if it does. So that's the topic, right? We're going to build the expression set from scratch. Your microarray experiment data, which is the cell file, and in our simple example, we're not processing cell files. So let's say you're processing a comma-separated file or a text file where you have your expression data, which is what I just showing you here. Let's say this is the data that you started with. So you have your columns of sample and your rows of features here. So this is a matrix, right? So you have F rows and S columns. Again, let's say you have F number of rows, which is 6 here, and S number of columns, which is 5 here, 6 by 5. So how do you first construct this particular assay data object, right? So you have to start from the scratch of what does R give you, right? So input here, when I'm trying to construct that assay data object, is my expression data.txt file. That's my input. So this is my file, right? That's my input. And my output is going to be a matrix type of an object. So you're already familiar what a matrix type of object in R is. And how am I going to accomplish it? I'm going to accomplish it by reading that text file, and I can use the function read.table. So that's what I'm going to do. So I can use this function read.table, right? That's going to and I kept my expression data, which is this one, under my C drive in R1 folder. Okay, so my expression data text is my C drive under R1 folder. It could be something different for you. So to know, first of all, how does read.table work, what I would do is I would question read.table, right? And it's good to open that app. So once you see that, that tells you exactly, right, what are the different parameters. So this, you can use a read.table, or even instead of a text file, if you had a CSV file, you can use the read.csv parameter. In the molecular weight example, I had a tab delimited file, so you're going to use the read.delim function, right? Then what's required is you have to tell them what's the file name, does it have a header, and there are some additional parameters which is always not mandatory, but then you have to read over here to see what are these additional parameters does. Do you have a use for it? Do you not have a use for it? And then at the very end, you can actually look at your some of the examples that they give you, how to process the file. So that's the help file, right? So in our case, first I'm telling you what the file is. My file over here has a header. With a column, the sample names. So my header is true. It's separated by comma. Very interesting. This file is separated by comma. Some files may be separated by tab. You cannot use an Excel file and use separated by tab, because Excel file is not separated by tab. When you save the Excel file as a CSV file, then it becomes a comma separated file. So make sure you understand these very basic things, how your files are saved. And row.names one means I want to import all the rows, and as is equals to true means if some of my column is coming as a number, I just want to use that as a number. If some of my column is coming as a character, I want to use that as a character. I don't want to do any conversion. But details of this, you can actually look into the help file like I showed you at read.table, and you can process it. So that's the first thing I do here is I read my text file. So, and then what I do after I read it, I try to convert it into a matrix object. So that's as.matrix. So now it's stored into an expression object. So what is the class of the expression object that you just created as matrix from read.table? So of course it is a matrix, right? Because that's how you did it, as.matrix. Now, what are the dimensions? So I showed you in my text file here, I have 6 rows and 5 columns. So, I've showed you many times. So you can just use the dimension function, gives you 6 rows and 5 columns. If you want to know what are the column names of your matrix, again, A, B, C, D, E, F, sorry, A, B, C, D, E, those are the 5 samples you have. And the row names will give you specifically all the features, that you had. Okay, so now so far you're still into the R space of just working with the matrix. Okay, so now extend this expression object from R basic object type of matrix to bioconductor object of expression set. Okay, so that's what I showed you, the high level diagram here. This expression set is an object. It's built out of assay data object. Assay data object is actually built out of your matrix object that you just created. Okay, so now how do you take this assay data, if that's the only thing that you had, right, but store it as an expression set object? Okay, and this is the best way I can explain. So the way you actually create a class, right, is by using a new operator. So before you do that, you have to import the library that you need. So the minimum information that you need to create the expression set object is the expression or the assay data itself. right? So you cannot have an expression set object when you have just the experiment information and what sample belongs to what condition. So if you don't have your actual text files or cell files, which has the data, you cannot do anything. So the minimum information that you need to create your expression set object is the assay data itself, and the assay data itself is a matrix type of an object. So as long as you have assay data, you can create that minimum information. You can convert that matrix type of object under assay data into the expression set object. But we will just go into more detail other than the minimum. So that's your minimum information that you need. And now if you look into the structure of that object over here, what you see is what you just created is the assay data. You have no information after pheno data because it's 0. You have no information there, so that's also 0. Nothing of feature data, so that's also 0. So all that it did is out of here you read the data from a text file, created a matrix. So now you have your assay data, and you made an instantiation of your expression set object by just using assay data. But the remainder of it, which is pheno data, feature data, experiment data, you supplied no information, so all of them right now here is showing as 0. But it is no longer, when you created this, it is no longer a matrix type of object, because you use this new parameter here, right, and supplied expression equals to exprs. This minimum set is actually now a expression set type of an object. Okay, so now let's build more pieces. Let's just not get stuck by just creating this assay data. Now let's construct pheno data, let's construct feature data, and let's construct experiment data. So what I'm going to do now, what I showed you earlier for the expression data.txt, where I read this as a read.table function and I converted into a matrix. Similar way, I can also create the pheno data. So my input here is pdata.txt. So that's my input. So again, just so you see again, this is my input file. pdata.txt is telling me which of my sample belongs to which of the condition, and what are the whether it was treated with drug or placebo. So this is simply a text file. So that's my input, and I'm going to read it using read.table. And this time I'm not going to convert it into a matrix. My output can just simply be a frame. And in my scenario of pdata.txt, this was separated by comma. But my pdata.txt file that I created manually, sorry, I don't know, maybe I closed it. The file that I created manually is actually separated by a tab. So this is separated by tabs, okay? And I have 4 columns here. So when I'm reading this file, it has a header and is separated by a tab, and that's what I'm showing you here. So that's pdata, okay? So now let's just see what pdata looks like, just exactly what was in my text file. So my pdata has these 3 columns, has the sample names, has the values. What is the class of pdata? Should be data.frame. Okay. The dimension, if you want to type it, it should have 5 rows and 3 columns. Now, one thing to check, and which is a good thing to check, the number of rows that you have here on your pheno data, which are your samples, there are 5 rows, that should actually equal to the number of columns that you had on your assay data. So if you forgot already, so let's look at what your assay data looked like. Your assay data was expression, right? exprs. So if you look at expression over here, so that was your assay data. So when you just started with just the assay data, the class of the assay data was actually a matrix. So over here in this matrix, I have 5 columns. So I want to check now that my 5 columns here in my assay data matrix is matching with the 5 rows that I have in my frame, right? So your frame, the way I constructed it, is a pdata is a frame. My assay data is a matrix. So ultimately my objective is to start with these objects individually and then construct the bioconductor specific expression set object. And that's where I'm going, and I hope to accomplish by the end of this lecture. But what I showed here in the middle is you don't need all those phenodata and experiment data to create the expression set object. But the minimum information that you need is your expression matrix. Just like in a function, you may have a lot of parameters, but out of those parameters, there's always one parameter that's an essential, and the other parameters are optional. So I created my up to my p data here. So now I'm checking that my rows in my p data, which is 5 of this A to E, matches with the columns in my expression set matrix. So this is a conditional check that I can do by all. So it says true. That means every single thing is matching up. This is just good to do a quality check. Now let's do a summary on my p data. So if I do a summary on my p data, it tells me that my first column is gender, which is type of character. The second column is, and let's just look at p data again. My first column is gender, type of character. The second column is also character between drug and placebo. And the third column is probably numeric, right? And that's what it's telling me. So I have gender, which is character, 5 of them. Numeric is the type. Character is also type, drug or placebo, and the score is numeric. Now, one recommendation that we give you here is when you have some phenodata over here, just like the way I'm showing you here, male, female, you probably don't want to store it as a character or a vector. You probably want to store it as a factor, because again, this is a categorical data. You have either male or female, you either had drug or placebo. So the ideal recommendation that the book makes you, and I'll probably throw this out in your homework, which I'm posting, is I want you to figure out a way where when you're importing the phenodata, the first column is coming as is a character, second column as a character, third column is number. That's how you have. But I want you in your homework to store the first column as a factor, the second column as a factor, but the third column I want you to keep it as a number. So I'll give you a little bit of hint how I would do that, which is if I were when I read my first phenodata in this particular one, I said as is equals to true. So what that particular parameter did is something was coming as a character, like gender, it kept as a character. If something was coming as a number, like a score, it kept it as a number. But what I can do is I cannot use that parameter, but I can use another parameter called call classes, mean the class of each of my column. And that can be applied to each of this column one at a time. But I'm showing you if I were to do it globally, right? So I'm saying my classes of each of my column, and here I have 3 columns, will need to be a factor. So if I do that, and if that's the way I read my p data, and now if I actually look at the classes, again, this is a function called sapply. Initially I showed you tapply, so make sure you understand the difference between sapply, tapply, eapply, and all those different ones. So I define sapply, so now you see everything is a factor, right? Gender is a factor, type is a factor, score is a factor. So in your homework, what I'm going to ask you is keep the gender and type as factor, but the score convert it into a numeric. Okay? But I just give you a slight hint, but so that's something you have to do. How you keep the first 2 as factor and the third one as numeric. So let's go back to our original way that I'm doing it. And now if I figure out what my classes are, there should be a character, character, and number. So I went from all factors back to again character, character, and numeric. So I want you in homework to do it factor, factor, and numeric. So you get an idea. Easy stuff. Okay. So, and again, I'm taking it directly from the Vignet. So what it's saying here that sometimes when you have this, now that we have covered the assay data and we have covered the phenodata, we maybe want to construct another frame called metadata, right? And what I mean by that, if you look at your p data here, right, it's telling me my gender is female, female, and drug is type is drug and placebo. Maybe I want to quantify my A, B, C, D sample times a little more, because when I look at it, I just really don't know what A means or B means, and I know what gender they are or whether they got a drug or placebo. But on top of my phenodata, I want to add more information. So I can store that information into a metadata based format. So let's see how we can construct a metadata object. Okay. So what we can do here is we can construct another frame where my label description here. So what I'm going to do here is, instead of writing gender, I'm going to give you some more qualifying information to say, this was actually a patient gender, and this was the status of, whether they were control subjects in placebo or they were treated with a drug. And the score really actually means the tumor progression on XYZ scale. So I'm just taking my phenodata and I'm supplying more information to that phenodata, but I don't want to alter the structure of phenodata itself. I just want to extend it by putting more information around it. So before we put this more information around it, let's just create a frame of what we want to put more. So I want to give those, the way I would do that is I would construct a data frame, and I will give the label description as the 3 items that I want to qualify more, and my rows will still be gender, type, and score. So let me just show you after constructing it. So once you visualize, it'll probably be a little better. So my metadata about my phenodata, and it's an interesting concept, but hard to visualize. So it's going to be gender, type, and score. So gender means patient gender, type means status, and score means tumor. So here I am not actually, in the first one I started with my assay data. Over here I told me in my assay data the sample ABCD belongs to this, this, and this condition. And then I want to put another frame where I'm saying, this gender actually means this, type means this, and score means this. You don't always have to do that, right? But if you have a need to further quantify or further give more information to what your phenodata mean, or whether you had a particular observation on your experiment and you want to store those kind of data in a very structured way, then you can actually create a metadata object. And that's what the metadata did. It's a frame. And now what I'm going to do, it's interesting, I'm going to put the p data and metadata together, and I'm going to have a phenodata. So what we can do, the biobase itself comes with a class called annotated data frame. So I'm going to make an instantiation of that class, and I'm going to say on that new instantiation of that class, my data is going to be the p data, which I created here, right? And my var metadata is going to be the metadata which further quantifies the gender, type, and score. So once I do that, and now if I look at my phenodata, right? Now phenodata consists of my metadata plus also the p data that I created. So it's just matter of putting your p data that you created here and your metadata that you created here. If you want to put those two together and create another object, that's called annotated data frame. So when you start to think of it, it's object on top of objects, right? So p data got created out of a frame, metadata got created out of a frame, and then p data metadata itself got rolled up to another object called annotated data frame. So that annotated data frame is now phenodata. So I guess if I do a class of phenodata, it should tell me it's annotated data frame. Let's check it out. Right? Exactly. So the class of this is annotated data frame. Similar way, if you did a class of your metadata, that should be a data frame. So that's what it is, the data frame. Similar way, p data was data frame. So I hope I made some connection with you guys, how you start with basic objects. Here it was a frame, here is a frame, put them together, then you create a new class called annotated data frame. And now out of those class that you have, which is phenodata, right? If I only want to access just the p data part of it, or if I only want to access the metadata part of it, then I have to invoke a method. or a function, so I can get this of what I want of a particular portion of the class. So PhenoData I know is a class of annotated data frame, consists of two other subset objects, but if I only want to get up to the PData or the data frame part of it, which is PData, I can just use PData function or a method on that class. So if I do that, I only get the PData. Okay. So now how do you subset more? So that's, I got just the PData out of my annotated data frame, and let's say I only interested in sample A and C. Okay, and I want to know what the gender is. So if you look at sample A and C here, both of them are gender female. So out of this particular PData that I have, how do I even subset only the samples A and C? So maybe I went from a class annotated data frame, right, to my subset of the object that was built off, which is PData. And from PData, I want to again get into more deeper level to get to a specific element of A or C. So that's how you're doing the subsetting here, right? So if you do that, and if you want to look at it now, that's an object, and if I want to get the subset of that, so I only get the subset of A and C where gender is male or female. So you have to sort of think through it, and speaking and listening to it, you probably are not making a connection, but unless you don't practice and see how I'm making this transition, how I'm going from one object to another object, it will be very difficult for you to know how the inner workings are. And if you take an approach of not understanding what the dependencies are and how things get built on top of one another, you probably should not pursue a coding type of an approach, or you should probably stick to a tool, because then it will be very confusing to you. I'm not trying to discourage you, but your frustration will come once you don't understand how one things get built from another thing, and how do you subset things, and how do you access certain things, because your homeworks will get more and more difficult. So if you don't understand how fundamental structures were and how you subset certain things and how things get built on top of things, it's going to be challenging, and that's what I have seen in the past with other students. So I'm emphasizing again, whatever I'm covering here, try to understand, try to practice, and ask me questions, how these transitions happen and what you did not follow. Okay, so we so far talked about, again, go back to our landscape picture of what we're trying to do. We talked about how we constructed this from the matrix. We talked about how we constructed this from the frame. And we talked about how you can actually add more metadata to the PhenoData. So we constructed a frame, we constructed another frame, we put that together, and we created annotated data frame, which is another class. So finally now we can talk about featured data and experiment data. And then we'll put all this four together and we'll create an expression set object. So let's talk about featured data here, which will be very simple, which is the simplest one, and I didn't make it complicated. The book didn't also. So for the featured data, all you're simply saying is that my chip type that I used for this sample that I got, which is this one, is done on an 8GU AV94 platform, right? So that's all it is. So that's my featured data. You can actually make it even more complicated, which you will in coming homeworks, and actually the packages do it for you, but you need to appreciate that, which is you will actually you have 22,000 features, right? So how do you know which features actually belongs to which particular genes? So the way they do that in these packages is they attach more metadata to it. They quantify each of this feature, just like the way I showed you on the metadata portion, what gender means, what type means, and what score means. So let me see if I can access it. I forgot, right? So what gender means, what types means, score means. It means these, right? So similarly, if you have your features here like AFX, AFX2, etc., I can also construct another metadata right? To say, actually, this one means gene 1, or this one means gene 2, right? Etc., etc. So that's how in future packages, and I think in lecture 4 you're already reading about annotation, so you can actually take it to a next level, and for each of your features you can construct the metadata and you can say which feature actually belongs to which particular gene, and that's already done for you in the annotation packages. But should you were to construct certain things like that, you would have followed the example I just showed you, how each of these columns over here were quantified further to say what it belongs. And you can add more and more column here. It's just a matter of in the data.frame you add more columns, right? So that's your feature data there. And I give you some note here, how you do that. And finally is the experiment data, which is again coming from the BioBase package, and this is already when I created this pheno data here, that was done from the annotated data frame object. That's actually done from a couple of the frames. This one just a simple text. Experiment data actually comes from a MIME object, which is minimum information about a microarray experiment. So you do that, and that object expects these are the different parameters, like what's the name of the lab, what's the contact address, what's the email. So this is some kind of a format that the community agreed that whenever you're submitting your particular cell file with your professor or in your lab or your job, you could be running some experiment, you have some cell files, now you want to upload it into Gene Expression Omnibus. So what's the minimum information you want to provide? So you and I, who are looking up those experiments, know what you did or who you are, and if we have question, how do we contact. So that's how you construct your experiment data coming out of the MIME object, and that's how you do that. So you can also look at your experiment data here. So I think now we created all the components, right, that we need to create our ultimate expression set object, which is going to be the storage of our cell files data. We haven't gone up to the analysis part yet, which we will do from next week and your homework and other parts. We're going there. But fundamentally, all we're trying here is to understand, how do I create the storage object. So we did assay data, we did this, we did feature data, we did experiment data. Now the final step is construct the expression set. So I like these couple of sentences that the authors say here. And you can appreciate my non-stop speaking for last hour and a half, and all that with the sensical and nonsensical things I said. After all this work, the final assembly is disappointingly easy, right? So again, you create that object by saying new expression set. So these are the parameters you supply. You need the expression, you need the pheno data, you need the experiment data, and you need the annotation. So all of them you have already constructed. So you just construct a class by doing a new, and your example set is done, right? So that's your expression set. So remember, when I first showed you the minimum expression set, which was, I believe, here. So let me go back. When I first constructed this, right, I created only on the expression, because I told you that the minimum information you need to at least tell them what are your cell files. Not necessarily you need the pheno data and who did the experiment and what annotation it features has. And when I created that minimum expression set over here, and when I looked at the structure, all of these things were 0, right? That object was expecting a pheno data over here, right? But it was 0 observation. Was experimenting data about your feature, but there was 0 observation. But now that I have created the pheno data, I have created the features, I have created the experiment, and finally constructed my expression set, which is not a minimum expression set anymore because it has all the other parameters there. So if I now look at the structure, it should no longer be 0. And I can verify that by now saying your pheno data, the data has 5 observations. Remember, we had 5 samples. Your feature data, meaning these features, there are 6 of them. So now you have 6 of them. So those things which were at the very early stage created just based on your assay data or EXPRS object in the variable the way I named it, None of those did populate. So at the end of the day, when I created the pheno feature data, all of them populated. So I hope that you make the transition to understand what was the minimum when I first created versus what other different things I needed to create. So now holistically, right, I have the complete picture of my expression set object. So anytime you want to get any help on your expression set class that you just created or what's coming out of the package, you can also write help expression set about the class. It will give you a lot of examples and everything. Sorry. Just like the question that you do on a primitive object, you can also use the help to understand the definition of the classes that you're just actually importing from bioconductor. So anything that I went over, what are the different properties or slots? So if that expression set object is actually made out of these different things, right, which should map up to what I am showing you at the very beginning of this text file, which is the description here, right? So that's how I created assay, pheno, feature, experiment. So if you now look at the help file here, that's what it's made out of. Actually, expression set itself is made out of eset, but let's not go there. So that's your slots or properties or sub-objects, whatever you want to call it. Method is what are the different functions that's available that you can use. So you can use write.expression to write out all the values that you have into a text file. You can convert something specifically to assay data by using exprs. So there's different slots and the methods that a particular class has, and what are the different functions that you can use. So for example, if you want to access out of your, so let's go back here. If you want to access out of your pheno data, which we created here in the annotated data frame, and let me come back here. Right, so I only, out of my annotated data frame, I only want to access the P data portion of it. Remember, annotated data frame consists of two subset of objects, which is the pheno data, which is a frame, and metadata, which is again a frame. So, but if I don't care about metadata of the annotated data frame, but I only care about P data, I use this function P data pheno data. And how do I know that this function even exists? So, right, so that's how I know is from my help function, because that's what it tells me, my P data, right? And that's, so these are the different functions of var metadata or pheno data or P data. So you have to sort of understand those functions from here, or methods, and then apply to your class. And what the class actually consists of, you can get from the slots. So try to understand what's the difference of slots. See these methods. And methods will tell you how do you actually access a particular slot. And within the slot, you also have subsets. So understand, you very, very critically try to understand what everything is made of, and try to break everything into smaller pieces so you can get to where you need to. Okay. So I think finally we're talking about some subsetting here. If you want to subset pheno data, just for gender. Okay, so this we already talked about. We constructed the whole experiment data here. We talked about help. And finally, I'm not going to go through it. It's already 7:36 because I want to take you through the simple AFI so you can actually get some idea about your homework. So I'll spend maybe another 10-15 minutes on that, and then maybe we can wrap up the class. So accessing data elements. So this is your example set, right, that you have, expression set that you constructed. So out of this expression set, if I am only interested, let's say, of my pheno data, which is the gender, right? So let's do that. So that only gives me the gender, right? Female, male, that you had in your pheno data. If I want to check some kind of condition to say that out of those, only when something is female, let me know. So you can just get true, false, etc. So you sort of have to play with it, right? But if I only, out of my example set, if I only want to know my feature names, but I don't care about the sample names, so I can use the method feature names, and the method and what you can, what's available or not, then you should look it up here under methods, whether you want to get just the feature name or sample names and etc. It's already available here. So these are some of the same examples that I'm showing you here. If I only want to know the sample names, that's how I can get it. So understand what the class is, what the class is made of, and how you can access different slots within the class by using different methods. And again, how do you subset, right? And that's, it's going to be all about that. I probably speaking too much about it, but I think you guys are all intelligent enough to understand what I'm saying. Again, if I only want to get just the my expression set that I consisted, again, right, consists of assay, pheno, feature, different things. If I only want to know the data out of my expression set, I can actually run this code here, which is I can cast it just to an expression, and if I do that, you'll see the mat or matrix will just look like what my original data set was. Here it is. So the example set, which is the expression set object, contains assay data, pheno data, experiment data, all that sub objects. But if I only care about the assay data, I cast it just by expression set, so that's what I get. If I only care about the pheno data, I cast it as pheno data, and let's see what I get. I get the annotated data frame, which is consisted of pheno data and metadata. So out of the annotated data frame now, if you only want to get the pheno data, but not the metadata, you should be able to do that. And maybe that's what I should ask in the homework. How do you grow from one object to another object, and then get to the very lowest level? And once you get to that, then how do you access either one frame or the other frame? And how do you access some elements maybe out of that frame? So that way you can navigate and transfers any way you want, and you know any state of any object. So what you're trying to access and what you're trying to do will not be a black box to you. So don't take an approach of a black box, and if you do that, it's going to be very confusing for you, and you're going to end up hating it. So I don't want you to hate it, but I want you to break it apart and try to understand what's coming from where. So I'm not going to do the rest of it. We only have 20 more minutes, or maybe I'll just spend another 10 or 15 minutes and help you through the part of it that's going to be actually definitely on your homework, that's going to be posted this weekend or tomorrow. So let me just see if you guys were still there. If assignment 2 done, the whole course is done using R. Okay. C++ is definitely harder than R. sorry, and all of those you can actually write to a table. So you can just look at the result here, and so that's also actually a little more complicated class, which has a slot of, it's different than expression set, but that's the implementation of simple Laffy. It has all the present absent calls. It has a slot of group members, so group is the treatment that you just did here, right? So that's one slot. The CLNO is the members, so it could be either L or O. The slot data makes sense. So you have 10 cell files, 5 of them lean, 5 of them obese, so that's another slot. And it has some annotation of what feature names are for each of those probes. So it's a little more complicated than the expression set itself, but that's the implementation of simple Laffy. So if you want to construct that from scratch and how pairwise comparison itself works, look up the code. It'll be a good exercise for you, and I recommend that. So now that you have this result, you can actually then take the different values from that cell file, from that class, and a very simple implementation for you to know out of these results what were the mean change, fold change, t-sticks, and whether it was absent or present. So you can actually use these particular columns names within a data.frame, which you convert to a data.frame, and that data.frame, by using the write.table function, you can save into a Excel file. Okay. So once you do that, very simply, everything that you did from your results, then you can just get your fold change, test statistics, and whether it was present or absent, and that gets saved on your mycom.excel. So now if you go back to your R1 folder, that analysis you just did now should have been saved. So now let's just open it and see what it did. I mean, one approach is for you to follow these different vignettes and do it blindly and see where things need to be changed by you. Not a bad approach. Start by that. But as you go through the course, try to ask, why did I put this here? Why was this object this way? And if you take that approach, you're going to become an expert in R. Then we're going to have you teach this class, right, instead of me. Or if you want to do it just by thinking what things you need to change, maybe it'll work for you, but I don't want to make any more comments. So that's what it did, right? So you had your features here. So it did a mean value for lean, a mean value for obese. It did the fold change, right, by subtracting the log of this from log of that. It did the test statistics, and I showed you the formula how to calculate the test statistics for two sample, but it already did for you. And for each of these cell files, it gives you a present and absent call, and it already comes from the AFI. So present means that intensity is available, A means it's not available, and M is I think it's missing, but I have to clarify that. I forgot. Someone asked me what M is. I don't think it's missing, or maybe it could be below threshold. So that's what that did, right? So everything that you need to do for your analysis, means, fold change, test sticks, so it's all there. But in the class, in the homework, I might ask you, now do this comparison where your test sticks is your t-test or your p-value is minimum 0.1, and you have a present call. So if you look at this here, your com file, that you have a present call in all 10 cell files. So this condition will probably not meet because your test is not 0.01, it's very high, 0.31. So it's not present in all 10 cell files because you have a call of M here. So this won't work. But if I lower the criteria and say, okay, give me something where it's present at least in 9 cell files out of the 10, and your t-test is at least minimum 0.3, or 0.35 or whatever, then this row will return, right? So that's the big thing here. So I'll give you some criterias, and then and depending on this criterias, you have to extract, what I'm requesting you to extract. So that's the code for that. And so it's a minimum present of 10. So in your case, if I tell you 8, so you'll just change it to 8. I have a 0.01 here. If I tell you the criteria should be 0.05, then you change it there. And then you can actually take that and actually write it back to a frame, and you can do some plotting, but you can practice this. I'll upload it. And in the homework, what I will do different is I will actually ask you to do some volcano plot, and you have to read some sections on your chapter. Maybe it was chapter 4, I think. So I think you'll have fun. So I'll try to combine the homework between how you do something from scratch and how you play with some data types and objects and how you convert one to another. And then I'll have you go through the simple FE. You'll have some opportunity to do some quality checks and QC and see how QC is done and how some plotting and volcano plotting is done. And so you have to start from what I went over this web session, and in my homework I will tell you what Vignet to use. I'll give you a lot of hints, so you just kind of have to put it together, and everybody in the past was able to do it. My students, most of it, 90% of them. I don't see any reason why you won't be. But I would like all of you to develop a deeper appreciation of how the objects are built, and try to not do things blindly. Try not to consult with each other. Don't copy each other's homework. If you do, it's going to result in a very bad grade for those who are copying. And try to enjoy, try to learn, and if you have questions, try to ask me. So 7:58, I'm going to stop the recording. We will meet again next week. And as I mentioned, that since my DimDim license